Welcome, welcome, 11 Chem. Today we're going to take a look at simple covalent molecules and how their structure and properties informs the properties of the materials that are made up of them. All right, I'm actually going to go through a little theoretical tool to help you predict the three-dimensional structure of small molecules. That's called the valence shell electron pair repulsion theory. Okay, so again, this is we're just wrapping up module 1 here at the start of the term. All right, and we're taking a look at the bonding topic. All right, and addressing the inquiry question to actually look at what binds atoms together. Okay, now simple molecules. All right, in the case of simple molecules, all right, their properties for the substances that are made up of them is determined by the shape of the molecules, the structure of the molecules, the forces between the individual molecules, and the forces between the molecules and other substances. Okay, so we can see down here we have the structures of water, ammonia, and carbon dioxide shown, and these are kind of like a variation of the ball and stick model. All right, but each of them does give you some indication of the three-dimensional structure of each of these molecules. All right, so I wanted to today spend some time showing you how you go from a formula to the three-dimensional structure. Now, to do that, you use valence shell electron pair repulsion theory. Okay, and this is a set of geometry based around electron pairs. All right, that actually explains the angle of bonds in terms of a central atom. And this works really well for small molecules of about 3 to 7 atoms in terms of explaining their geometric shape. All right, and it's actually quite important for later on, okay, because the geometry of small molecules actually affects how they interact with light. And that actually ties into our final year 12 topic, which looks at spectroscopic means of interrogating organic molecules. All right, so VSEPR theory, or valence shell electron pair repulsion theory. Okay, we'll call it VSEPR for short. All right, like the bike. All right, this explains the shape of molecules using knowledge of the valence electrons that surround each of the atoms. Okay, now because electrons repel each other, and we know that electrons in filled valence shells, which is what's happening in the case of the small covalently bonded molecules, all right, we know that they pair up in a suborbital. All right, okay. Those pairs of electrons in the suborbital will try and stay as far away from other pairs of electrons as possible around that central atom. Okay, and so what that means is that electron pairs surrounding atoms can actually be thought of in one of two different ways. There is what's called the a bonding pair, all right, which is the pair of electrons that make up a covalent bond. All right, one of the sticks on the ball and stick models pictured at the bottom of this slide would be representing one of these bonding pairs, okay, or an unbound pair of electrons. These are known as lone pairs, and these are often not represented in these ball and stick models. It's a major problem with the use of these models. Okay, all right, but you need to understand that the shape of each of these molecules is not only controlled by the bonding pairs of electrons, but the unbound lone pairs of electrons that are not bonded. Okay, and so this is where understanding the valence electrons is really helpful. Okay, so when it comes to applying the valence shell electron pair repulsion theory, what you need to actually do is you need to, 1, draw the Lewis structure of the molecule, 2, count up the number of electron pairs, all right, and then from the number of electron pairs, you determine the arrangement of atoms around the central atom of the molecule. And you're able to make reference to, all right, diagrams like the one on the right of this slide, which give a number of common molecular geometries that are all verified by looking at the ways in which these molecules interact with light. All right, these include linear for molecules that occur in a straight line, trigonal planar for molecules that only have 3 pairs of electrons in their outer shell. All right, okay, and we have tetrahedral, which is what a great deal of molecules are actually going to be. And so, in fact, most molecules that we explore, all right, will actually involve tetrahedral, trigonal, pyramidal, or the bent shape just there. And you can actually see the lone pairs are represented on this molecule just here, here, and here. Okay. All right, so what we're going to do right now is we're going to take a look at how you would actually go about doing this with 3 examples, and later in the week when we have our Q&A, we're going to go through a number of additional examples. All right, let me clear this off, and let's take a look at our examples just here. Okay, so we're going to start with methane for our examples just here. Okay, and let's start by drawing the Lewis structure for methane. So we have 1 carbon atom and 4 hydrogen atoms in a methane molecule. All right, so remember our carbon atom has 4 electrons. All right, and each of our hydrogens, each of them has 1 electron. So what's going to be going on in that Lewis structure is we're going to have 4 covalent bonds. Let's circle that in just here. All right, we're going to have 4 covalent bonds surrounding that central carbon atom. Okay, and so what's actually going to be going on is we have 4 bonded electron pairs surrounding that central carbon atom. All right, so if we consider what's going on just here, okay, all right, we have our central carbon, and surrounding that we have 4 electron pairs that are going to want to be as far apart from each other as possible. Now, to do that, if we take a look at our examples on the previous slide, we can see that the shape that will form is tetrahedral. Okay, so you'll end up with 1 pair of electrons that are bonded vertically above it. All right, and then you'll have 3 prongs off the bottom of the carbon. Okay, now when we are talking about a structure of a 3-dimensional chemical molecule, like a tetrahedral structure like this, okay, because our hydrogens in the bottom, our 3 prongs, and they're shaped a little bit like a caltrop, which, if you're familiar with this from kind of like history from the times of knights and so forth, this was a very cruel device that they would throw in front of people on horses to actually injure them, because when they fall on the ground, 3 prongs always point at the ground and 1 is always pointing up, no matter what the direction is. Now, what we're actually looking at just here is a way of drawing this so we have 3 different orientations in the page of our 3 bottom hydrogens. All right, and so the solid wedge just here, okay, I'm just finishing coloring in just here. That means we have a hydrogen poking out of the page, and the dashed line wedged just at the back here means we have a hydrogen going into the page. Then we have 1 just out to the side. Okay, so that is indicating that we actually have a 3-dimensional shape. And so if you think about this in terms of being the shape of the outer outer edge, we have essentially a three-sided triangle with each of those corners being a hydrogen atom. Okay, and in the middle we have our carbon. All right, now let's take a look at our ammonia. Now, unlike carbon, ammonia has a nitrogen surrounded by 3 hydrogens. Now, nitrogen, unlike carbon, has 5 electrons in its outer shell. Okay, so in that case there, we have, let's just start putting electrons around that central nitrogen atom. Okay, because we have 5 electrons, okay, we have a lone pair. So this is a pair of unbonded electrons. And surrounding that, we have our hydrogens, which they form 3 bonded pairs of electrons. Okay, so if we take a look at this, all right, so we have 3 bonded pairs of electrons, and let me just get a different color just here, and we have a lone pair of electrons just here. All right, so in terms of talking about the 3-dimensional structure that's going to form just here, all right, let's start by drawing our nitrogen. Here we go. Minor technical issue. All right, so let's start by drawing our nitrogen. We'll draw our lone pair. All right, now remember we have 3 more pairs of electrons, and they want to be as far apart as possible. Okay. And so what ends up happening is they form a very similar structure to our tetrahedral methane. Okay, we have 1 hydrogen coming out, 1 hydrogen going into the page, and our 3rd hydrogen off to the side. And above that at the top here, we have our lone pair of electrons. Now, the shape of this molecule is trigonial pyramidal. Okay, and what's actually going on here is if we were to think about each of our pairs of electrons, okay, all right, all we've done is we've taken away our top hydrogen, okay. All right, that's all we've done. And so by taking that away, and we're still filling that space with a lone pair of electrons, the shape of the molecule is still affected by that lone pair of electrons. Okay, so even though we have a different shape, we still have 4 pairs of electrons surrounding that nitrogen. Okay, makes sense? Now, in the case of water, if we look at the Lewis structure for water, we have our central oxygen atom. Now, oxygen has 6 valence electrons. So if we consider the electrons surrounding that central atom, we actually have 2 pairs of unbonded electrons. And when we put our hydrogens in, what we can see is we have 2 bonded pairs of electrons. Okay, now this actually tells us about our structure of our molecule, just the Lewis structure itself. Okay, all right, because if we look at this, we have our central oxygen, and off each side we have a hydrogen. Okay, and we have 2, let me just fix that up because it's atrocious. we have two lone pairs of electrons that take up space. Now, if we were, and this is where the picture doesn't actually translate very well, if we were to look at this as a three-dimensional object, all that's happened here, and I'll just switch colors just here, is that essentially if we come back to our tetrahedral molecule, is that we have just replaced two of these hydrogens with lone pairs of electrons in the case of water. All right, and we end up with a bent molecule. All right, so you actually see just here, we're able to, as long as we pair up these electrons surrounding that central atom, we're able to make predictions from the Lewis structure on the three-dimensional shape of the molecule once we know some of those basic geometries of those molecules. All right, now in the notes and in the lesson outline, I have an exercise for you to do, which is a bunch of Lewis structures for some simple covalent molecules. All right, I've got the answers there ready for you. Have a go, and we'll go through those in our Q&A lesson. All righty, thank you for watching this short little video on VSEPR and how to apply it. All right, so I'll see you in our Q&A lesson. All right, give it a go, and let's get to it, people. All right, next time. See ya.